So to continue our discussion of vapor pressure, remember vapor pressure is the pressure of the vapor above a liquid. So even if you have a glass of water sitting out in your kitchen that you forgot about, there is water molecules at the surface that are evaporating, that are turning into vapor. And if we contain that vapor, it then exerts a pressure. So that's what we mean by vapor pressure. And essentially, the relationships that you want to understand with vapor pressure is that as we increase temperature, vapor pressure increases. This is what this graph over here is showing us. And you know this if you're heating up a pot of water on the stove, you have a lid on the pot, and as the water gets hotter, the vapor pressure increases, and sometimes that lid will start to rattle because of that. So as temperature increases, vapor pressure increases. And as the intermolecular forces increase, meaning the forces between molecules increases, the vapor pressure decreases. So as an example, water has a very high intermolecular force, hydrogen bonding. The water molecules really like one another and want to stay connected to each other. So because they have a high intermolecular force, water's vapor pressure is generally low. Water is not volatile. It doesn't have an odor. Whereas something like rubbing alcohol has very low intermolecular forces. So the vapor pressure for rubbing alcohol is high. It's an inverse relationship. And you know that because rubbing alcohol has an odor, or something like fingernail polish remover or gasoline. Those all have very low intermolecular forces, so their vapor pressures are high. Temperature and vapor pressure is a direct relationship. Intermolecular forces and vapor pressure is an indirect relationship. Now the boiling point is the temperature at which the vapor pressure equals the atmospheric pressure, or the external pressure. The atmospheric pressure is essentially the weight of the air on top of us. And we have about a 50-mile column of air on top of us, and it weighs about 14.7 pounds per square inch of everything on the surface of the planet. So that exerts a pressure. And when the vapor pressure of a liquid matches that atmospheric pressure, that's when a substance starts to boil. Now, the normal boiling point for anything we assume to be at 1 atmosphere of pressure, and 1 atmosphere of pressure is what we consider to be normal atmospheric pressure, or average atmospheric pressure. And we're going to talk a lot more about atmospheric pressure in the next chapter. But essentially, water boils at 100 degrees Celsius because that's the temperature at which water's vapor pressure matches the atmospheric pressure. And if we go back to this slide right here, this dotted line here represents 1 atmosphere of pressure. It represents the average atmospheric pressure. So water down here, let's say at room temperature, has a very low vapor pressure. But as we heat up the water, the vapor pressure of the water increases, so that at 100 degrees Celsius, and this dotted line right here represents 100 degrees Celsius, the vapor pressure of water matches the atmospheric pressure. And that's when water boils. For this diethyl ether here, the vapor pressure matches the atmospheric pressure at a much lower temperature. I believe it's in the 70 degrees Celsius range. So that's the strict definition of a boiling point. And so as the atmospheric pressure increases, the boiling point of a substance increases. Now here's the practicality of this relationship. If you were to go out to Colorado, up into the Rocky Mountains, the atmospheric pressure is a lot lower than it is here at home because you're higher up into the atmosphere. Let's say you're on top of a mountain that's 12,000 feet up. That's 1.5 miles higher than what we are here in Indiana. So there's a lot less air on top of you, meaning the atmospheric pressure is lower. Water boils at a much lower temperature at the top of a mountain than what it does here. because the atmospheric pressure is lower. So the vapor pressure doesn't need to be as high, which means the temperature doesn't need to be as high in order for water to reach the boiling point. So the boiling point is different at all points in the world dependent upon the atmospheric pressure, dependent upon your elevation. Higher elevations, boiling point decreases. At sea level, the boiling point's a lot higher. And this 1 atmosphere of pressure is said to be the average atmospheric pressure at sea level. So as atmospheric pressure increases, the boiling point increases. And as intermolecular forces increase, so does the boiling point as well. Because if you have higher intermolecular forces, those molecules don't want to separate from each other. And in order to become a gas at the boiling point, they need to separate. So both of these relationships between boiling point, intermolecular forces, and the atmospheric pressures are direct relationships. When one goes up, the other one's going to go up. Next thing we want to take a look at here are phase diagrams. And phase diagrams tell us under what conditions of pressure and temperature is the substance going to be a solid, a liquid, or a gas. And so as we see here generally on this diagram, this area here, and by the way, this is a phase diagram for water, this is when water is going to be a liquid, when it's between these temperatures and these pressures. Anywhere in here, it'll be a liquid. Anywhere in here, it'll be a vapor. And anywhere over here, it'll be a solid. Now notice that we can have water vapor that is below the freezing point. Here's 0 degrees Celsius. This is the freezing point of water. And here's 100 degrees Celsius. This is the boiling point of water. We can have water vapor down here that's below the freezing point as long as the pressure is so very low, as long as we lower the pressure. And we can also have liquid water that's above the boiling point as long as we increase the pressure. So you can have liquid water that's nearly 400 degrees Celsius, that is 373 degrees Celsius, well over 3.5 times the boiling point, as long as we have an increase in pressure. So this is what a phase diagram tells us. And on here you see the normal boiling point, which is right here, which we just got done saying was taken at 1 atmosphere pressure. So that's the normal boiling point right there at 100 degrees, and it hits this line right there. If we increase the pressure, then we're going to increase the boiling point. This triple point down here is an interesting point. This is the point at which a substance can exist in all 3 phases at the same time. It can be a solid, a liquid, or a gas. And if you look on the resource videos in Canvas, there's a video of a substance at the triple point, and you essentially have a skim of ice forming on the top of the water while it's boiling underneath. Pretty cool. So what you want to be able to do with this phase diagram is just understand, given a certain pressure and a certain temperature, be able to read if it's going to be a solid, a liquid, or a gas. A couple other vocabulary terms up here. This critical temperature, this is the highest temperature that a substance can be a liquid. So the critical temperature of water is 374 degrees Celsius. Above 374 degrees Celsius, water will always be a gas, no matter what the pressure is going to be. The critical pressure is the pressure that matches that critical temperature. And above that critical temperature, we can raise it and raise it all we want, but the substance is still going to be a liquid. So there are some vocabulary terms. Now this is a phase diagram for carbon dioxide. And you'll notice here that carbon dioxide at 1 atmosphere pressure, and this is normal atmospheric pressure, what we live at, notice that as we increase the temperature, it goes directly from a solid to a gas. Carbon dioxide sublimes. It is dry ice. Frozen carbon dioxide is dry ice. And this is the example that I gave earlier when we were talking about sublimation. And this shows us, yeah, it goes directly from a solid to a gas at normal pressures. In order to get carbon dioxide to be in the liquid phase, we need to increase that pressure 5 times what normal atmospheric pressure is. You see 5.1 atmospheres and above, then we can have liquid carbon dioxide, but not under normal conditions of pressure. So every substance has a different phase diagram. And this is a phase diagram using those vocabulary terms for phase changes that we talked about at the beginning of the chapter. So when something's going from a solid to a gas, it's subliming. Gas to a solid is deposition. We have your melting and freezing up here between a liquid and a solid. Remember, we talked about these vocabulary terms in the video of the notes before this. And then here's a phase diagram for water as well. And just be aware of all the vocabulary that goes along with these phase diagrams. And then the last thing we want to talk about here is water. And what makes water so cool? Water is a weird molecule. Water should not do the things that it does. But it's great that it does the things that it does, because that's why we have life here. This graph shows you how hydrogen bonds to the other elements in oxygen's group, like tellurium, selenium, sulfur, and then here's oxygen, H2O. Now, we've talked a long time ago about group trends. And the trend for the oxygen group bonding with hydrogen, the boiling point starts up here with hydrogen bonding with tellurium at like 0 degrees Celsius, and then hydrogen, selenium at -50. And if we followed this trend, water should have a boiling point of -68 degrees Celsius. 68 degrees below zero is when water should boil. And well, that would be bad for us because there would be no liquid water here on the planet. But water instead boils at 100 degrees Celsius. Notice this trend goes down, 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 and all of a sudden, boom, goes up here. It has an abnormally high boiling and melting point. And the reason is because of hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular force. And hydrogen bonding only occurs when hydrogen bonds with oxygen, fluorine, or nitrogen. And so because of that hydrogen bonding, water molecules like to stay together. And because they like to stay together, it takes a lot more energy to get them apart, i.e. a lot more heat for them to turn into the gas phase or another phase period. So because of that hydrogen bonding, water has an abnormally high boiling point. And if you look here with hydrogen fluoride, the halogens, hydrogen iodide, bromide, goes down, 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 and then all of a sudden, boom, goes up here the hydrogen fluoride. The same thing with ammonia. So because of hydrogen bonding, water has an abnormally high boiling point and allows water to be a liquid when it normally shouldn't be at given temperatures. And it's essentially because of hydrogen bonding that life exists here the way it does. Now, the other unique property of water is that its solid phase, ice, is less dense than its liquid phase. And that's because when water forms ice, it forms these hexagonal patterns. And notice there's a lot of empty space in here between the molecules. That causes ice to be less dense than liquid water. And ice and water is one of the only few substances, it might be the only substance, where its solid phase is less dense than its liquid phase. But that's a great thing, because then ice floats on ponds and lakes, which allow aquatic life to exist there during the winter. If ice was like anything else, it would freeze on top, fall to the bottom, and in certain ponds and even some small lakes might freeze solid. If you're a fish, that's bad. So that's another unique feature of water.